All right, we'll get started here. So this talk's a little bit different from the conference talks I usually give. So this is not a hardcore technical talk. So if that's what you came for, maybe you want to go hear Alex's talk in the other room. Seriously, I won't be offended if you go. This is so it's a little bit of a fluffy talk. It's about the how we think about the decisions we make in developing and stewarding products, and it's about our perception of time as software engineers. So, the timescales in which our products live and, how we think about planning software products is very different from a lot of other industries, and I think we kind of have a bit of a distorted sense of time as software engineers. For example, the highest technical title in a lot of organizations is architect, right? And historically, architects build things like bridges and buildings. And in theory, software should last longer than bridges and buildings, right? Where software is immune to things like uncooperative weather and geology. But in conventional architecture, making buildings that could stand for 1,000 years is something we knew how to do like 1,000 years ago. And in software engineering, 5 years seems like a long time. So why is this, right? We're not even dealing with the real world, and yet, we can't build things that last very long. And I think, a lot of the focus in what we do is aimed at building things for solving a problem today, not to stand for 1,000 years, not even necessarily to stand for 5 years. But the reality is that successful systems live for longer than we initially imagine. And and when we're working on systems that have been successful and been around for a while, we spend a lot of time adapting them to meet new challenges. So, for example, the system that I work on is pretty old by comparison to most software systems that people are still investing in now. This year, Java is 20 years old. And for the last 5 years, I've had the privilege of piloting the evolution of the Java language. And so this talk is kind of a few thoughts, of what I've learned, from the challenges of evolving a mature platform that has millions of users, and some lessons I've learned along the way, and a little sneak peek on where Java is going next. So, Facebook CEO Mark Zuckerberg advanced this motto in the early days, for the Facebook engineering culture: move fast and break things. And he was basically telling the team it's more important to make progress on improving the user experience today than to worry about preserving what's already there. And this phrase may have started at Facebook and certainly didn't stop there. I'm sure you've heard it in the halls of your own organizations. And not only is this part of the culture of most startups, but if you listen carefully, you'll hear some developers implicitly assume that this is just a basic fact of software engineering in general. Now, it's not surprising developers are drawn to a catchphrase like this. After all, breaking things can be fun. And breaking things is also a lot easier than improving them without breaking them. And, the parts that slow you down are often the boring and unglamorous parts. And so who wouldn't want permission to ignore all the boring parts? But it's also easy to take this too far, and some people do. And it's even possible that if you think that progress requires breakage, you might even start to confuse breakage with progress. I don't know if anybody knows anybody like this, but I've certainly met people who think that. And of course, this really isn't about breaking things, right? It's about building things. Breaking things is rarely a good thing on its own. I mean, usually it comes with some kind of consequences, legal or financial or what have you. So the intent of saying, go move fast and break things isn't endorsing vandalism. It isn't celebrating destruction. It's about creating the opportunity to do something better. And without necessarily slowing yourself down by the need to preserve the status quo. So in other words, it's about giving permission. And that's a good thing, because giving permission to value what could be over what is now, which is good as far as it goes. So, giving people permission to break things so that you could build something better in its place is not really expressing a technological or social viewpoint as much as an economic one. So Zuckerberg was, whether he knew it or not, appealing to the work of the economist Joseph Schumpeter, who coined the phrase creative destruction to describe the inevitable fact of capitalism that progress always comes at the expense of what came before, that the growth of new industries inevitably brings about the decline of old ones. So it's kind of notable that Facebook doesn't say this anymore. And last year at the F8 conference, Zuckerberg officially retired the old motto and replaced it with a much less catchy one. And what he's saying is, yeah, progress is still important, move fast, but not at the cost of destabilizing what's there now. So what changed? Well, it's kind of obvious what changed, right? When you're a startup with no users and a bare bones product, the economics all point you towards make a lot of progress fast, because otherwise you're out of business. And it doesn't matter what the collateral damage is or how much technical debt you accumulate, because if you don't make progress fast, you're going to run out of money, you're going to get scooped by the competition, and it's game over. On the other hand, when you're the market leader and you have a mature product, the economics all point in the other direction. You don't have as far up to go, and you've got a lot farther down to fall. So it's not surprising startups are more concerned with progress than, while more established businesses are more concerned about stability, and Bob Dylan said as much, 40 years ago, when you ain't got nothing, you got nothing to lose. So move fast and break things is a sensible strategy when you're a plucky startup and you're hoping to rise above the crowd and get some attention, and less appropriate when you have 1 billion users. So the point of all of this is the priority balance between progress and preservation is a business decision. Move fast and break things isn't a philosophy. It's not a strategy, it's a tactic. And it's a business tactic. Hopefully it's a tactic supported by a sensible cost-benefit analysis. So one thing that I think separates sort of the grown-ups from the kids is the understanding that programming is, at heart, an economic activity. Technology is fun, it's exciting, I love programming, and we're all lucky we get to do this for a living. But it's a mean to an end, it's not the end itself. If it was cheaper to build Facebook out of rubber bands and duct tape than out of PHP, then that's what they would have done. And I know what some of you are thinking, right? You're thinking PHP basically is rubber bands and duct tape. Might be true, different talk. But the point is, like any other activity, we can measure, or we can at least try to measure, the inputs and the outputs. And the inputs in programming are pretty simple, right? You got programmer time, you got pizza, right? That's all it takes. And the outputs are harder to measure, but hopefully in any successful scenario, you're going to get some working code, and you're probably going to accrue some technical debt, which you can think of as the obligation to provide more programmer time and more pizza in the future, assuming you stay in business. So moving fast and breaking things is a conscious choice to get more of both of these outputs. More working code, more technical debt. Okay? And for a given amount of pizza, I want to get more of both of these outputs. I can't get more working code and less technical debt very easily, but I can choose to get more of both, and that's okay. And like I said, when you've got nothing to lose and your investors are breathing down your neck, it can be a very smart choice. But again, this is a business decision, not a technical decision. So it should be based on the business conditions, and those change over time. It's not a philosophy. So by moving fast and breaking things, you're choosing to value time to market over stability and over future maintenance cost, and sometimes that's a sensible play. So to hammer this point home, I pulled a few quotes from a great article I found by Jocelyn Goldfein called "The Right Way to Ship Software." And I'll skip to the secret. There's no right way to ship software, right? It all depends on business context. But here's some quotes that I thought were compelling. In a profession where we carry out decade-long spanning holy wars over tab widths and capitalization, it's no surprise people get attached to their development and release habits, right? And but if shipping so much software has taught me one thing, it's to be agnostic. Different methodologies optimize for different goals, and all of them have downsides. If you maximize for predictability, you're going to lose out on productivity. So she ends with a plea. My fellow engineers, please stop asking, is this process good or bad? And start asking, is this process well suited to my situation, right? And Goldfein is, whether she knew it or not, appealing to the philosophy of Charles Saunders Peirce, sometimes called the father of pragmatism, who in 1878 coined this very wordy bit, which is now known as the pragmatic maxim. But to summarize it, it means being pragmatic, and we're engineers, we'd like to think of ourselves as pragmatic. Being pragmatic means judging a thing by its effects on the world around us, not on their innate properties, not on whether it's beautiful or not, or just or good or not. How does it affect the real world? And one might imagine that, person term was appealing to the work of a much earlier philosopher from a galaxy far, far away, who might have said, "There is no good, there is only good for." And if he had said this, what Master Yoda would have meant was, as engineers who are supposed to be pragmatic, we need to be willing to look past our own aesthetic beliefs and principled beliefs about what is good or bad and judge things on the basis of whether they work. And they work in the real world, not the world in our heads, right? And we rather than judging, something on the good, whether something is good on its innate properties, based on what is it good for? Does it move the ball forward? So in that light, what do we think of this move fast and break things strategy? Well, as should not be surprising at this point, both good and bad are the wrong answers, right? The right answer is, it depends. Is it right for the situation? So, and this kind of leads me to the main part of my talk, which is about my own experience engineering down at the bottom of the stack and how that differs from what most of us are probably used to. And one reason why this might be more relevant than you think is as our careers progress, we tend to move down stack. And that's not because we're making a conscious choice to move downwards, is there's a lot of stack growing above us. And so if you stick at the part of the stack which is your comfort level, where you are relative in the stack will move downward over time. Yesterday's middle of the stack is tomorrow's bottom of the stack, and it's like, you look around. I did some quick Google searches for like Java software stack diagram, right? So I found, a couple of random diagrams. The point is so this one is like the Oracle middleware stack. Java's way down at the bottom there, right? Bottom of the stack. And like this one is the Spring stack. Again, where's Java? Right there at the bottom of the stack. And that's actually not really the bottom of the stack, right? There's a whole bunch of stack below us, right? There's the hardware, and there's the operating system, and there's virtualization, and there's containers, and all of that. But it's the bottommost part that's visible to most developers in their programming model. So, the point is about being, down at the bottom is when you're the platform that everything depends on, moving fast and breaking things is a really lousy strategy. Because down here, the term for breaking things is bug. Right? And when you have millions of users, there's no such thing as no one's going to notice. Everybody notices everything. So, necessarily, when you're at the bottom of the stack, you have to place a very high priority on stability and compatibility. And, there was a time in Java's history when it wasn't the bottom of the stack, or even part of the stack. That's even longer ago. And in those days, we did move fast and break things, right? There were a lot of incompatible changes between Java 1.0 and 1.1. And, there was a lot of churn in the language and the libraries and the JVM design, especially leading up to the first release. And even, a few years after. But, success comes with a price. And that price is you got to stop breaking things. So when we talk about not breaking things, obviously we're including don't break our users' code. But, our aversion to breaking things goes a lot deeper than that. The people part of the story matters as well. So we don't want to break our users' expectations. We don't want to break their confidence in the platform. We don't want to break their mental models about how things work or the value of the investments they've made in technical skills. So each of these forms of people compatibility also places constraints on our ability to evolve the platform, evolve the language, evolve the libraries. And, my job is, to shape the developer's view of what Java is. The user visible part of the programming model, the languages and the libraries. And, there's no shortage of, let's call them helpful suggestions that I get from developers about which way we should go and what features we should add. But I think there's kind of a disconnect between what I do and what people think I do. So I made some fun little charts to illustrate the difference. So this is the funny part of the talk. So this is what one possible view of what an industry-focused language designer might do as viewed through the eyes of our academic colleagues. So in this view, my job would mostly be about the technical aspects of language design and creating more expressive type systems and adding features that lets us express more kinds of programs safely or make the intent of a program more clear and all that. And yes, this is all part of my job. I'm not saying I don't do any of this stuff. But it totally omits the human side, which is, I think, the more interesting and the harder part of it. So when we're doing, a particular group of features, of course, we have a time budget and a dollar budget. But we're also mindful of what I like to call the complexity budget. So a complex feature might allow you to do cool things. It might allow you to express some interesting, valuable new programs, but it might also do a lot of damage, either directly through misuse or indirectly by distracting the developer, from what they're actually trying to accomplish, right? Which has nothing to do with programming languages and features, but has to do with delivering business value in the context of their organization. So keeping things simple means that a feature can actually be used and used correctly by real people. And even simple ideas or otherwise sensible features, are things that we have sometimes discarded on the basis of cultural constraints because they're too disruptive to existing mental models, of developers. So I'll give you a quick example of from the Java 8 days. And so in Scala, if you have something that inherits multiple traits, and traits can have behavior, you can have a conflict between multiple traits, and Scala resolves them by linearization. Scala says, if I say I'm extending A, B, and C, and there's a conflict between B and C, B wins because B came first. Totally reasonable way to do it. No way on earth we could do that in Java for resolving conflicts between multiple default methods, because Java developers have 20 years of experience that say the order in which you declare your supertypes don't matter. And we can't change that. That would pull the rug out from underneath everybody. So these are the kinds of considerations that someone coming from an academic programming language background might never think about or might not take seriously. But when evolving a platform that's used by so many people, they become pretty important. So this chart is a lot less charitable and therefore more fun. And this is what you may have seen this in another talk, I've reused these, but this is what I sometimes think people in the community think I do based on what they say. And it bears some structural similarity to the previous chart. If you proceed from the top, you've got your secret backroom meetings. And then every once in a while, you poke your head out of the secret back room and you make some obnoxious comments on a mailing list, or you come to a conference and make some self-promoting comments, right? And from a technical perspective, it's mostly about stealing features from other languages, and of course, lots and lots of discussions about syntax. Now, it's fun to complain about how people don't understand what you do, right? But it's also important to realize that they're the people we're doing this for. So in some sense, success looks like, not correcting the wrong ideas about how things work, but just making it work better anyway, right? James Gosling described Java as a blue-collar language, a language for working programmers to get their jobs done. And there may be a lot of rocket science in designing it or implementing it or evolving it and certainly in specifying it, but you shouldn't have to be a rocket scientist to use it. And when I say use it, we have a pretty wide range of users in the Java community, and we don't want to alienate anybody because we don't want to lose sight of where's the mainstream heading. So the guys who are way out front today, the high frequency trading guys, for example, it might be easy to say, well, those guys are outliers, but they might be tomorrow's mainstream. So we can't really afford to alienate any of the users. So, here's a chart that's a little bit closer to reality, at least from my perspective, about what we do when we're evolving Java. And, again, there's some structural responsibilities. We renamed the smoky backroom quadrant into internal responsibilities, right? We renamed the self-promoting slice into community, right? So this is the more manager-acceptable version of the previous chart. But the technical focus is very, very different, right? It's not really so much about adding features as much as keeping features out. And users are always saying, we want this feature, we want that feature. Users never say, take this feature away, right? But in reality, adding features, language features, is really the last thing you want to do, because every feature adds some bad weight. Every feature may interact with any other feature that we've done in the past, or any other feature we might think about doing in the future. And we have to choose them really carefully because we're going to be living with them for a long time. We don't take them away. So, my favorite example, of course, is serialization, right? Serialization has interacted with every feature we've added since then. In the process of doing Lambda expressions in Java 8, we spent literally hundreds of hours of analysis and discussion figuring out how do we make these things serializable, what's the limits of serialization here, what are reasonable expectations for serialization. And the result wasn't perfect. It was a lot of compromises, and I'd kind of like to have some of those hours back, actually. So, many of the remaining slices deal with the consequences of how features interact with each other. And a common misperception is that the hard part about adding a language feature is implementing it in the compiler. I kind of think of that as like that's the first 0% of the work, right? All of the real work comes from figuring out, is this the right feature, fitting it in around the other features, analyzing its interactions and testing for compatibility, and not just with the features you've got, but the features you might think about adding, which is a pretty big set, right? And analyzing the compatibility consequences of everything, and that's like the biggest slice of what we do. The fun part here, that's this little tiny slice at the bottom. What would James do? Right? You get to do that about 1% of the time. The rest of the time is, less exciting. But the big slice in the previous, in the previous chart is compatibility. And compatibility comes in a lot of forms, and we're obsessed with all of them, right? So the most important form of compatibility is binary compatibility. That means if I have existing class files and I update some part of my program, I drop a new jar on the class path, will the call sites embedded in those class files continue to link, right? Because in Java, all method invocations, all field accesses are dynamically linked nominally at runtime, right? So when a class file has a reference to a member in another class, the signatures have to match up between the two class files, or you'll get a linkage error. Now, most people aren't aware of this, which is amazing, because that points to just how well it works, right? It works so often that we don't even notice it. But when class A calls a method in B, we record the signature of the selected overload in A's class file, and it better match exactly with the signature in B's class file. Otherwise, we get an error. And this is like one of Java's secret weapons, because this is what enables you to take a new jar, drop it on your class path, not recompile anything else, and have things still work. But it's a pretty strong constraint. Class files that were compiled in 1995 should still run today, and they do, and that they will still run in 20 years. So that's binary compatibility, but that's just the beginning of the story. So we've got source compatibility. Will clients or subclasses continue to compile and mean the same thing after a change? We've got behavioral compatibility, right? Does the code continue to do the same thing after a change? Behavioral compatibility is kind of a weird one, right? Where sometimes, if you fix a bug, that's not behaviorally compatible, but you don't want to not fix bugs, although some bugs we don't fix because people are relying on the old behavior. And then there's all these like other forms of compatibility, like serialization compatibility of, can I serialize an instance of an object on an old platform and deserialize it on a new platform and get a valid, instance. And, then there's, it gets even more subtle from that, like, footprint and memory characteristics and performance characteristics and all that. And there's this deep cross-cutting concern that cuts across all of these compatibility issues, which is separate compilation, right? We rarely recompile the whole program. We recompile part of the program. Every time you put a new library on your class path, you have recompiled part of your program. You've just outsourced the recompilation to your library provider who compiled something, and you put that on your class path without recompiling the rest. So we always have to deal with the possibility that only part of the system has been recompiled. And normally this isn't a problem if you follow some reasonable rules for evolving library code, like it's okay to add things but not remove things, right? That's kind of obvious. But separate compilation shows up, when you, for example, change your compilation strategy, your code generation strategy, or when the generated code for a given class depends on information from another class file. This shows up in Java with bridge methods. There are times when you do, very rare occasions when you do have to recompile because a bridge method is needed. But it happens very rarely. You do see a lot. You see a lot of this in the Scala world because the compilation strategy for Scala is under much more rapid evolution, and as a result, you end up with recompile the world requirements much more often. But when we're looking at features, it's happened in the past where we'll say, this is a great feature, nope, we can't preserve compatibility and implement it, so we're not going to do it. And like I said, that's not to say that we never violate any compatibility ever, because like I said, we couldn't fix a bug without breaking behavioral compatibility. But we have to go through a fairly rigorous, quantification process to determine, well, how much code would break if we did this? How important is that? And do a cost-benefit analysis. So, a lot of people think we're nuts, right? How can you guys be so concerned about compatibility? But from our perspective, there's really no other responsible choice, because with like billions of lines of code out there, any incompatible change is going to break someone's mission-critical code. And, it takes a certain kind of arrogance to say, yeah, you should break his code, because his code sucked, and it'll be for his own good. We do get these suggestions a lot, and I don't think they're being arrogant. I think they're being helpful, but the mistake is they're only focusing on part of the picture. And the part of the picture that that I'm talking about here is, I think a lot of developers tend to overestimate the importance of code and underestimate the importance of stable programs, right? So that developers, this makes sense, right? Developers stare at code all day long, right? So they have well-developed sense of what is good code and bad code and how to make code better. But it's kind of like one of those optical illusions where depending on what part of the picture you look at, you see a different answer. And so like when users look at a language feature, they say, they're imagining all the things that they could do with that feature and how it would change their code and how they could express programs that they can't express easily today. When we look at a language feature, we're not thinking about your code, we're thinking about everybody's code, right? We're thinking about how might it be used, but also how might it be misused? How might it interact with other features? How it might change the style in which developers program? How migration of existing code to new features would cause other subtle changes in whether those changes are good or bad. So we're thinking not just about the code that's in front of us, but about everybody's code, and that's a very different perspective. So at this point, you might be getting a little depressed, right? You're probably thinking, gee, it's impossible to make any progress at all if you have all of those constraints. And, maybe the sensible thing to do is don't move at all so you don't break anything. Well, it's a guaranteed path to compatibility for sure, but it's also a recipe for slow irrelevance. But, the good news is evolving things compatibly isn't impossible, it's just harder. And it's like working in any other difficult environment. You have to approach the situation, with the proper precautions, the right training, and the right safety equipment. So, it's not hard, just suit up. Okay. So let me go through a couple of examples of sort of some of the tricks that we do for evolving the language without breaking compatibility. So if it's not acceptable to change the meaning of an existing program, a language designer's next best trick is to expand the range of valid programs, to assign meaning to programs that previously were invalid. So, and ideally what you'd like to do is add features that abstract over other features, right? So that the existing features just become special cases of the new feature. Because instead of adding a completely new feature, by extending an existing feature to a broader range of situations, it's less jarring for users to absorb the new feature and learn what it's about. So we want to build on users' existing mental models of how things work. And this is also less likely to create strange new interactions if you're extending an existing feature. So we call this strategy embrace and extend, which is shouldn't have the negatives associated with how this phrase was used 15 years ago. We actually think it's a good thing. The hard part is coming up with a sensible set of semantics for the enhanced feature, such that when restricted to the conditions that where they were previously valid, they match the semantics that you already have. So let me give an example of this. In Java 8, we added default methods, right? So if we were starting from scratch with multiple inheritance of behavior, we would probably not have ended up with default methods. We would have ended up with something more like traits, right? And we would have had a different set of rules for resolving conflicts between declarations of the same method in multiple supertypes. Just to summarize briefly, and I think you probably all know what default methods are by now. So previously, interfaces could only contribute type information and members, but in Java 8, we enhanced them to also be able to contribute behavior. So, in the old model here, when D extends C and implements I, and both C and I have the same member with the same signature, they basically get merged, right? So there's only one M in D, and it overrides the M and C and the M and I. Now, in Java 8, we could add a default. And now what happens here is potentially we might have a conflict. When we're trying to figure out what members D has, we might say, but wait a second, I could be inheriting behavior from either C or from I, right? But we want adding a default here to be a binary and source compatible operation. Part of the whole point of adding default methods was to allow us to compatibly evolve interfaces. Because interfaces often come in a different maintenance domain than your program, right? They come from libraries, so you're not going to recompile the whole world at once. What we don't want is to have added this default here to I and have this be a conflict that breaks D, right? That would be brittle, and that would mean adding defaults to existing interface methods wouldn't be source compatible. So what we did here was we used a standard evolution trick, in order to make it so that the code on the previous slide wasn't broken. And the trick is we adjust the rules to give priority to the old interpretation of the world. So when we're resolving conflicts between multiply inherited members, we apply, this is in the new rules, we apply 3 rules, right? So the first rule is if there's a conflict between a superclass and a superinterface, the superclass wins. And this simple rule is basically step 1, do the old thing. Does the old thing work? Then we're done, right? And this gives us absolute compatibility with existing code, because if it worked before, it works exactly the same way no matter how many default methods you add. And then, the second rule is if you have 2 interfaces and one extends another, you take the more, the more specific. That's pretty easy. And rule 3 is, well, there's no rule 3. If there's any other kind of conflict, the programmer gets to resolve it explicitly. But this is an example of what I meant by adjusting a feature to fit in with other features. The rules that we arrived at, that implementations in interfaces are just defaults, and they only come into play when there is no implementation in the class inheritance hierarchy. This is probably not what we would have chosen if we were designing the language from scratch. But that's okay, right? This is also a perfectly sound and sensible and understandable model, and there's more than one reasonable way to design a programming language. This is one of our best tricks, is add new features so that they take up space that was previously invalid. We did the same thing and when we added autoboxing in Java 5. So basically we added a new implicit type conversion from int to integer, right? That seems harmless. What could go wrong? Well, what could go wrong is, what if before I had an overload where m takes int against m takes integer? Before, that was something that was unambiguous. But with autoboxing, that might now be an ambiguous overload. So what did we do? Well, we jiggered the overload resolution rules to say, well, first do it with the old rules. And if that comes up with an answer, then we're done. And then, if there isn't a single answer under the old rules, then we apply some new rules that involve boxing conversions and var-arch conversions and all of that. I call this strategy embrace and extend, because first you embrace the existing semantics, and then you can generalize from there and find something that both stands on its own and matches the existing semantics. So this is like one of our best tricks. The previous example with default methods, that one worked out pretty well, and we were pretty happy with the result. But, it didn't spring fully formed from day one. And in fact, it took 2 or 3 years from the time we first cooked up the crazy idea of, what if we could attach default behavior to interface methods? And the time we arrived at a sensible model that Java developers would look at, and not say, what the heck is this alien contraption that you nailed onto the side of my spaceship? Well, some people say that no matter what, but the point is, if you're lucky, your first idea barely works, but it's very rarely the right thing. So we went through many iterations of the design process, and each one seemed an improvement over the previous one, but it probably, like in this case, wasn't until we got to the 6th iteration or so that we got it down to something simple and clean enough that I could fit the rules on one slide. The insidious thing is, because each iteration was better than the previous one, at almost any point, we might have made the mistake of thinking, oh, we're done, right? This is so much better than it was last month. And in reality, it often takes a lot of iterations to find the right idea. And more than once, I had to tell my management, we're not there yet. It's going to take longer than we'd hoped it was going to take. And thankfully, the answer was always, well, take the time and get it right. Because when you're contemplating something that you're going to have to support for 20 years and is going to further constrain everything else you do in the next 20 years, you don't want to get it wrong. But I recently came across this quote from Steve Jobs, which I think really echoed our experience, certainly in the things that we did in Java 8. And he's got this really nice metaphor here about the middle. And when you start looking at a problem and it seems really simple and you have these simple solutions, you don't understand it yet. And your solutions are too oversimplified, they don't work. And then you get into the problem and you see, wow, this problem's really complicated. And you come up with all these convoluted solutions. And that's the middle. And that's where most people stop. And the solutions tend to work for a while, but the really great person will keep on going and find the key underlying principle of the problem and come up with a beautiful and elegant solution that works. And the really hard part about what he describes here is realizing that you might still be in the middle part. Right? Because when you're in the middle, you feel like, well, I finally understand this problem. I've been beating my head against this problem for months or years, and it's really complicated. And of course the solutions are going to be complicated. And it's not obvious that there's a better answer lurking inside. And it's incredibly tempting to say, well, I've got something that works, and it's simpler than the thing I had yesterday, so I must be there, right? Declare victory and stop. Complexity is insidious because if you know the problem you're trying to solve is complex, it tempts you into thinking, well, you have to accept a complex solution. And then, on top of that, you may be dealing with forces, saying, well, we got to ship this in December, right? And push, which can often lead you to think, well, what we have is not so bad. A sort of more extreme example of this, things take as much time as they take, was generics. A couple years ago at Java 1, James Gosling told a story about why generics weren't included in Java 1.0. And it's not because in 1995 we didn't understand parametric polymorphism. And it's not because we thought it was a good idea to have a static type system that was so weak that you would put typed elements into a collection and not retain their types when they come out, right? It's not like we thought that was a great idea. It's because we didn't know what the right thing to do was. And if we had pushed forward anyway and said, oh, Java has to have parametric polymorphism, what would we have gotten? We would have gotten like C++ templates or maybe patterns from Beta. And I think we're all pretty glad we didn't get those solutions. And it might have taken a long time. In fact, it did take a long time to get generics. But the generics we got were a lot closer to the spirit of the language than what we would have had in 1995 if we had slammed something in. So, the takeaway there, and James has said this to me so many times, if you don't know what the right thing to do is, well, that's okay, but please don't do the wrong thing. Just do nothing. Because if you do nothing, you have a chance to come back and do the right thing. And sometimes that means being okay with doing nothing. So, another way to say this is reality hardens like concrete. Before you do anything, there's a million paths forward. Once you do something, you've closed a lot of doors. There's not as many paths forward. And this is true for little things as well as big things. So you should always be aware of what doors you're implicitly closing by making a decision. So, a related aspect of the previous lesson is it's really tempting sometimes to think, well, I can get away with punting on the hard cases. And when you feel tempted to punt on some case that's too hard, that's a big red flashing light that you're in the middle and you're not done yet. In language design, this is so important because today's compromise becomes tomorrow's incomprehensible irregularity, right? So if you solve the easy cases and you punt on the hard cases, you can convince yourself, well, at least I made things better. At least some of the cases work. Before, none of the cases worked. But irregularity breeds complexity, and complexity distracts programmers from the work that they're actually trying to accomplish. And so, the kind of shortcuts that get suggested, like, well, just make a restriction so you can't do X when Y happens, right? Each of these adds complexity and distracts users from doing a good job. And they become tomorrow's, what could those guys have been thinking, kind of questions. So this next bit of advice probably feels like a little bit like the opposite of the previous one. So the previous one says, don't accept irregularities because building a regular solution is too hard. On the other hand, we should really be skeptical of the inclination to do anything for consistency reasons. I mean, consistency is good, it's a reasonable guide, but too often we allow our desire for superficial consistency to replace a deeper analysis of the problem. And my experience is, in all of the discussions we have on like OpenJDK mailing lists about what we should do and blah, 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 the most poorly thought out suggestions are the ones that start out with, for consistency, you should do X. That's not to say that consistency is bad or they're wrong to like consistency, but when people use consistency to justify something, it's often a sign that they don't have anything else to justify it with. So when you hear yourself doing that, stop and think and say, do I have a real reason for this? And it's pretty useful. Now, everybody knows this, the Emerson quote, but it's often misquoted, and it often leaves out the most important word. The most important word is the second word. Consistency isn't bad. Foolish consistency is bad. So think it through. Make sure that you know how to separate the sensible consistencies from the foolish ones. So, all right, I'm going to close up with just a little bit of a sneak peek of where Java is going, because this stuff is really cool, and I've been working on this for the last couple of years. So how do we pick our evolution targets for Java? What we like to do is to try to look at what are the pain points, what's making people unhappy, what's holding developers back, pick the biggest one and hammer down on it, right? So in Java 8, the point we picked was pretty much was language driven, which was improving the ability to abstract over behavior using lambda expressions. That was pretty successful, I think. In Java 9, the big pain point that we're working on is that of programming in the large and reducing the pain of assembling large applications out of modular components, and both modularizing the platform itself and applications. But pain points can also come from changing hardware, and we want Java to continue to perform well on the moving target that is modern hardware. And so let's take a look at some of the ways in which hardware has changed in the last 25 years, and the short answer is, well, a whole lot. So in like the very old days, we had these simple systems, single core, single socket systems with no cache, no pipelining, no instruction level parallelism. And in those days, it was really easy to estimate performance. You could basically count instructions, right? An arithmetic operation cost the same as a memory fetch. And over time, our systems got more complicated. So they went from single core systems, with uniform memory. We started to add caches. We started to add more levels of caches. We went to multi-core chips. We went to multi-socket. We went to NUMA. And as these systems got more sophisticated, the cost of a memory access got less and less predictable. So, if the data is in L1 cache, you might be able to have your data in a couple clock cycles. If the data is all the way out there in main memory, that might be a couple hundred clock cycles. And at the same time, our cores got fancier. They have deeper pipelines and superscalar execution. And so if a cache miss, because you have to go all the way out to main memory, costs you 300 clock cycles, and you can issue 4 arithmetic instructions per clock cycle, that means a cache miss could potentially cost you 1,000 instruction issue slots. So compare that to 30 years ago, right, where there was no such thing as a cache miss. A data fetch and an arithmetic operation cost the same. Now the worst case difference between them is a factor of 1,000, right? That's a pretty big change. So it stands to reason that given these changes in the underlying cost model, whatever trade-offs we made in 1995 about how to lay things out in memory are pretty unlikely to be optimal for today. Right? We could have gotten incredibly lucky, done things incredibly stupidly 20 years ago, and had them be perfect for today. Well, that's not what happened, right? So if you think about the type system that the JVM has, it's pretty simple. You've got your 8 primitive types, you've got classes, and you've got arrays. And this is flexible, right? You can model anything with this. But the flexibility isn't exactly where we want it to be. So primitives are pretty rigid, right? If 32-bit integer doesn't do what you need, it's not easy to make new ones. And objects are really flexible, but they're often too flexible. And the big problem is in 1995 we bought into this object-oriented orthodoxy of everything should be an object. Objects should have identity. Made perfect sense in 1995, but it was a little optimistic. So why do objects have identity? Identity serves two things. It serves mutability, and it serves polymorphism, right? Now, not all objects need mutability or polymorphism, right? Like, what people call, most like Pojo-style objects. They don't use inheritance, and a lot of them are immutable, right? But they have an object identity whether you want it or not. And JVMs have gotten really good at slicing through code abstraction, but they're not really able to slice through data abstraction very well. I mean, we poured a lot of effort into escape analysis, and it works okay in the good situations, but it falls off a cliff pretty hard when you push it a little too far. So the problem is the VM can never figure out when an object is never going to use its identity, so it can't optimize it away. Any object could be used as a lock by any code at any time. And so the VM has to be pretty pessimistic in the way it lays data out. So let's illustrate this. Imagine you've got a simple tuple-like class, like an XY point. And your class is immutable and final, so it's not polymorphic. It has no need for object identity, but you get fries with that whether you wanted them or not. And so let's say we make an array of these guys, and the array has an object header, and each element is a reference to another point, and each of those points is an object with its own object header. And so how are we doing on memory efficiency? Not so well, right? We've got 2 bytes of data payload for each, 2 words of data payload for each point. We've also got 2 words of header and a word of pointer. So that's like 150% overhead. That's not so good. These objects are allocated on the heap, which means work for the allocator, work for the garbage collector. And once garbage collection happens, they're not even going to be co-located in memory. But the real cost comes from traversing these pointers, because each of those pointers is a potential cache miss. So if I'm traversing an array events, right, I get great locality. I march down the array, I pull the first one into cache, it's already pulled like the next 7 into cache. And by the time I'm like on the second or third or fourth one, the prefetcher has kicked in and it's pulled the next block into cache. So I'm able to actually use my CPU for computation rather than waiting for the memory subsystem to cough up data. If I have an array of objects like this, I'm probably going to cache miss on every one of those dereferences. And as I just said, cache misses are expensive. Now, maybe this is not a problem. Maybe your data set is small. Maybe your performance requirements are modest. This is actually true for the vast majority of Java programmers, that the performance is good enough. But if you're doing high-frequency trading or big data analytics, or graphics, this is going to cost you a lot, and you didn't really ask for this layout, right? When you said I wanted an array of points, you would have been just as happy or happier to get this layout, but that's not what the JVM gave you. So, when confronted with a situation like this, what do developers do? Well, often they take matters into their own hands. Sometimes they have to, sometimes they just can't help themselves, and they do ugly tricks like this, right? Who here has seen people do this? Right? And so, what have we done here? We've shredded our points into 2 arrays to get locality back. But this code is harder to write, it's harder to read, it's more error prone, right? And the sad part is, sometimes people do this, for performance reasons with no actual evidence that it's actually, their code isn't fast enough or that they actually need the performance boost. But regardless of whether we do this, out of some genuine need or out of some destructive obsessive compulsive disorder, the winning move is to stop putting developers in a position where they perceive that they have to trade between good abstraction and performance, right? If we can give them good abstraction and performance at the same time, they won't do things like this, right? So that's the goal. So, this is a feature we're working on. It's a JVM feature that will bubble up into the language, which we call value types. And so by recasting our point as a value, what we're saying is, I don't care about identity. I'm willing to give up mutability, I'm willing to give up polymorphism, and by giving up that flexibility, we gain the ability to treat this like a value. So values, like ints are values, right? They're not stored on the heap. They don't have an identity. Equality is defined based on whether they encode the same number or not whether they're at the same address in the heap. They can be passed by value. You can pass them in registers. You can push them on the stack, etc. And that means we can also flatten their state into arrays, and we can flatten them into other objects. So we get both a more memory dense and a more locality friendly object layout. Now the cool thing about values is just because they have these nice memory characteristics doesn't mean that we can't abstract with them. They can have all the same thing classes can have. They can have methods, they can have fields, they can have constructors, their methods can be private, they can be generic. And because there's no polymorphism, dispatch is like static method dispatch, which can be fully inlined. So our mantra here is codes like a class, behaves like an int. Best of both worlds. And what's this good for? Well, there's an obvious long list of things this is good for, right? Alternate numerics, 128-bit ints, complex numbers, tuples, algebraic data types like optional or choice, cursors, all sorts of things that this is good for. Now, one thing to note is there's no new expressiveness here. This is a pure performance thing, right? This doesn't let you do anything you can't already do with objects, but it lets you do them without worrying about the cost. And as engineers, we have a tendency to worry about cost even when we shouldn't, right? Because we're wired to think about this for better or worse. And so by having the right thing be the fast thing, we remove a whole source of friction from the development process. And value types, because you can use encapsulation like you can, just like reference classes. You can use them, for example, as secure cost-free wrappers around sensitive data, where you're getting all this type safety, but you're not paying for an additional level of indirection. So safety, maintainability, and performance. Free lunch, right? Woohoo! So, okay. I talked about how features interact with each other, right? Here's a good example. We're adding value types. What about generics? Well, right now we have this uneasy compromise where you can generify over anything but primitives, which is almost all the types, right? There's infinitely many reference types. There's only 8 primitive types. So you do that quotient and you get 0, right? So you can generify over almost anything. If we added value types but you couldn't generify over values, well, that'd be terrible. Right? We could have our points, but I couldn't have an array list of points. That'd be awful, right? So this is an example of you add one feature and another feature is almost forced to come along for the ride. But when you look at how generics work today, we have the exact same layout that we had with our point example. It's even worse because there's only one word of payload here. So an array list of integer has all of these integer objects, all these pointers, too much allocation, no locality, too much indirection. And this isn't this isn't what the programmer wanted in the first place. What the programmer wanted in the first place was this, right? So the uneasy choice we made in 2004 about not being able to generify over primitives, when you add value types, kind of starts to fall apart. And so, we're finally going to close up that gap, which is a tremendous amount of work, I promise you, and do generics over primitives and values. It's actually probably about 10 times as much work to do generics over values than it is to do values themselves. But we're working on it. So these two features, value types and generics over values, are kind of part of a bigger effort that we're working on to reboot the JVM's relationship with memory, try to balance the need for abstraction and encapsulation with the performance reality of modern hardware. But the cool thing about this is, we figured out how to do this compatibly, and it's like teaching an old dog new tricks, which is really cool. So I'll wrap up, and then we'll have a few minutes for questions. I'll close with a quick warning, which is be careful what you ask for. We all want the software we write to be successful. We want it to be used by people for many, many years, but success brings with it constraints. And these constraints are largely about keeping the promises you made to your users, whether you made them explicitly or not. And they force you to spend, but the good news is they force you to spend a lot more time up front thinking about what's the right way to evolve the system. And most of the time thinking deeply about things before you do it, pays off, even though it means you can't rush forward quite as quickly as you might otherwise want to. So anyway, thanks for listening, and like, don't break anything on the way out, I guess. All right, thanks. So we have about 5 minutes for questions. I'm happy to take questions. Anybody? Yeah, over here. Just shout out your question, and I'll repeat it for the camera.
Do you guys use any tools or some other sort of process when you're trying to figure out if a proposed change will break compatibility with existing code?
Yeah. So the question is, what tools do we use for analyzing whether something is going to be a compatible change? So we do a lot of real-world corpus analysis. So we've got a corpus of probably 20, 30 million lines of Java code that we have accumulated from Oracle internal products, open source projects, Eclipse, NetBeans, all the Apache projects, blah, blah, blah. And we have we built this test harness where we can take an instrumented version of the compiler, run it over the corpus, and then have it generate events that get logged off somewhere, so that we can do things like say, how often does this pattern show up? Right, and we use this extensively in making language design choices. For example, like in Java 8, there was a difficult decision point about lambdas of, can lambdas only be converted to interfaces, or do we also want to convert them to abstract classes? You might think the obvious answer is, well, of course, you want to use it any place you can, but the abstract class case brought a lot of extra complexity. We did an analysis of use of single abstract method interfaces in the corpus, and we found it was like under 1%. So that gave us the confidence to say, you know what, we're going to draw this feature line here because we get all of this extra simplicity and we only inconvenience this 1% of the other cases. So we use it for both analysis of feature soundness and also for compatibility. Anybody else? Sir?
Can you give us an example of a really great feature that you punted on?
An example of a great feature that we punted on. Oh, putting me on the spot here. So many ideas come and go that it's hard to pick one. I'm sure I'll think of one after the talk is over. Sorry. Any other questions? All right, sir, over there.
What's the balance of feature ideas that end up shipping that come out of your team at Oracle versus come from the community?
So the question is, the feature ideas, where do they come from? Do they come from externally or do they come from internally? At this point, it's kind of hard to tell, and let me explain why. Because so in the Sun days, we had a pretty rich process for people to suggest feature ideas, when I started at Sun like 11 years ago, there was already a database of things that had been requested that would have been another 10,000 years of engineering effort to implement. And I would say that for things that people suggest, for the ideas that aren't outright dumb, there's about a 99% chance that they've already been suggested before. If something is if something is interesting, it's likely to have been suggested, to occur to many people at many times. That said, a lot of the, since a lot of the hard work comes from, analysis of compatibility, almost all the implementation choices and the should we go this way or that way come completely internally, because there's almost nobody out there in the community that has spent 4,000 hours thinking about the problem and is really able to, to speak to the trade-off. So the surface features come from everywhere, but I would say, of the features that are, have been suggested, we're not going to do 99% of them, not because they're not good, but just because we have to pick so carefully. All right, any others? All right, thank you very much.